So what we're looking at here is called a sine and cosine wave, which we are able to graph in math. It's really the same wave, but where it starts, the positioning is slightly different. So these waves, we're going to talk about waves for a little while, and more importantly to me is where they come from, because the waves actually come from a circle. So when you plot the coordinates around a circle, every position of that green dot going around, you get an x and y value that you can graph on a normal graph. And by doing that, when you graph it, it'll actually make a wave. So a wave is actually, when we express it in math, the coordinates around a unit circle. So there are many things, and we'll name just a few that have to do with waves. Obviously, we hear of sound waves. So a lot of these same properties apply. The way that it travels through molecules in the air and the vibrations. And so these waves, when they're a little bit higher frequency, the wave will be a little faster. And the lower frequency, is actually a slower wave. So the way the wave travels, it will go into the ear, and the smallest bones in your ear with this spirally shape, we see that spiral again, that's another one of the shapes I love. Your ear will actually have the bones vibrate in the cochlea, and it will allow you to hear the sounds. So the sounds that we hear are really vibrations that we are getting in our ear canal. Another thing we see is obviously all visible light is a wave. We'll look at electricity in a second. It travels the same way. Light has the interesting property of having both wave properties and particle properties, like little packets of energy. So another thing is light. So the light waves we see are also traveling in waves, and there's light that we can see. That's the visible light spectrum, and that is just this area here. And then we have X-rays, which are way smaller rays that go through things but not in our body, like our skin and our muscles, but they don't go through the bones. And even smaller than that are gamma rays. So they are 10 to the negative 15, I don't know if it's meters, I suppose it says here. So, gamma rays and X-rays are just energy waves that are smaller and smaller so they can penetrate through your bones. Then you have infrared. We have equipment now that can see infrared, and bugs will see an infrared light, and microwaves, which we use to cook. So those are larger waves. They said, I think your microwave, one wave is like almost halfway through your microwave oven. That's why the microwave oven spins, because the waves aren't small enough to penetrate all of your food. So to make sure everything gets warm, you got to spin the plate around as the waves go through it to warm it up. And then we have radio waves. I remember there are FM waves and AM waves, and the AM waves are so large that they can't penetrate through a tunnel. So that's why AM radio, you lose the signal when you go through a tunnel. So these are the spectrum of waves, and we'll take a look at the ones we see. So when your eye sees colors, and we have the color spectrum like a rainbow, what we actually see with our eyes, in your eyeball, there are these little nodes here, these little cones. And you see the cones shaped that are red and green and blue are the only colors of wavelengths that we see. We see red, green, and blue. The other colors we see is when the waves mix together and our brain simply not predicts, but figures out which color we're looking at. And these longer little things that look like a stick or a lightsaber, those are the cones that pick up when things are too dark, they pick up black and white. So when things get darker, like in 5, 6 o'clock, the sun's going down, it's darker, we see things in black and white. So that's why when things are dark and the light's not on, there's still some light, but it's not visible light where we can see colors. So we see shades of gray. Now the interesting thing about, these are what the cones look like. The interesting thing about the colors that we see is that things work in the opposites in the color spectrum. And you could watch many videos on YouTube about any of these ideas. These are just to kind of expose you to them. So the color wheel, if we take the color wheel that we use even in artwork, it kind of can help us explain what we see. So when we see a red rose, you're seeing not red, the color red, or the vibration of the waves of red. You're seeing something, the rose itself, the petals that are red, are absorbing all of the colors, especially green. And so you see red. So really you're seeing something that's reflecting red to you. So it's absorbing all of the colors and reflecting red. It's not itself red. So when you see something that's blue, a blue car, for instance, you're not really actually seeing a blue car. You're seeing a blue car absorbing all of the light, especially orange, and reflecting the color blue to you. So the car itself is not blue. It is reflecting the blue color light to your eyes. So it's kind of an opposite. So again, you can watch a video of how we see color or how the color wavelengths work to know more about that, or sound waves. So we have the color spectrum. And again, we have the different waves. So the waves get stretched out. The microwave, just less than one period. And then infrared, it's just 2 waves and then more waves. And it's just an example. Gamma rays are way smaller and they're traveling kind of like a high-pitched sound. It's a faster wave with more little waves going through. It has smaller period, you would say, in mathematics. So, light travels through a wave as well. And, the blue is the electricity. So we'll talk about electricity for a second. Electricity travels, but always perpendicular to it in a wave is the magnetic field. So the magnetic field and electricity is perpendicular to one another. Whenever there's electricity, there's magnetism, and wherever there's magnetism, there's electricity. And you could look up experiments on that. I myself believe that magnetism is going to be the great thing to explore in the future. We know a lot about electricity, but very little about magnetism. So you can kind of see it moving here as electricity is traveling in a wave, and it kind of even showing how the circle here is creating the wave. We saw that a minute ago. We'll look at it again. So how does electricity travel, and kind of why does it travel in a wave? Because these atoms here represent the copper wire. So when you have some electricity traveling through a wire that you plug into your wall, what's happening is the packets of energy, it's a little bit of chemistry. They take the atoms of copper, and the outer shell is called the valence electron. So the valence electron jumps off of one atom of copper, goes on to the other one, spins around and jumps off of that one, and then goes on to the other one. And it continues like that, and it travels up and down the circles into a wave, up and down the atoms. So electricity also travels in a wave. So we can see that waves are used in many of the different things. Gastronomy is the study of smells, and smells and things in the air also travel in a wave. If you've ever seen smoke coming off of an incense, it kind of floats around in wavy little patterns. So once again, the waves, the sine and cosine waves, we learn about sine and cosine, and we learn about a triangle. So if I were to stop this, let me see if I could do that for 1 second. If I stop this at any position here, what we could do is we could make a triangle out of it. And what we study at first in mathematics, and later, beginning in Algebra 2, we start to study the waves. But before then, we learn the triangles. So when you stop at any position here, you can draw a line straight down, and you have a triangle. So the sine and cosine and the degrees that we study in geometry so far, if you actually combine them all together, all of the coordinates all the way around will give you a wave. So in studying triangles, you're really looking at one spot on a circle. And when you look at all of the spots together and graph them, you will get the wave function, the sine and cosine wave function. And if we wanted to make the sound higher or lower, or different sounds or different colors, right, we would either stretch out the waves to different periods, or we would make the waves higher or lower, stretch them up real tall or stretch them really short. That's called the frequency. And again, you could learn more about period and frequency of waves if you look up a video on YouTube. So this is kind of what I was saying. If you take any of these coordinates, any spot on a triangle, you're really analyzing a degree angle and an x and y coordinate, the sine and the cosine of it. And when we graph all the way around and put them on a graph, we have the sine and cosine waves. So you can see that waves are really something interesting, and it's interesting to me how everything seems to always relate to circles. We live on a circular planet. All of the atoms of everything that's material here on Earth, from a human to a rock, is made of atoms with circles, and things like electricity are traveling in waves. We have stars in the heavens, and they spiral around kind of in waves. We even have a wave on the double helix in our DNA. So the circle helps us to understand waves and to graph them and to represent them in math, which allows us to do all these wonderful things like understand color and create devices that could read infrared and allow us to understand electricity. So there's a magnificent thing in not only waves, but in that powerful circle. There's something powerful about circles. But that's a little introduction about waves and what they do and where they come from and some of the places we use them, but there are many more. So hopefully you explain. Another interesting one, a rainbow. Why does a rainbow form, and why is it spread into the different color spectrum? What happens when the sunlight, it's all of the different color spectrum combined, the white light will hit either a prism. Prisms have the triangles, regular triangles in them, or it'll hit a water droplet. And what happens is called refractions. It bends the light, and in bending the light, it spreads them out into the different frequencies of red, orange, yellow, green, blue, indigo, and violet. So because a water droplet is round, it's eventually going to hit 42 degrees somewhere. So a rainbow comes from a 42-degree reflection off of a water droplet in a refraction. It then gets bent, and it spreads out into the different color spectrum. So we can see that the different wavelengths change. Blue light and violet have 380 to 450 nanometers of wavelength, and that increases with red, 620 to 750. The frequency also changes. The terahertz reduces from violet to red, has 400 to 484. Violet has 668 to 789. And the photon energy also. The violet and blue have more energy, and it reduces the amount of energy as we go down the rainbow. I believe someone had told me that someone took a prism and bent the light into the rainbow and actually took the temperature of each light. That was the first, one of the first experiments to begin to understand the different energy in the different colors. So, the different colors are produced by different wavelengths, and the violet wavelength will be a faster frequency. It's got more energy going on, and the red will be a longer wavelength. So, talking about waves a bit. An interesting thing that really goes along with this is the fact that every element on the periodic table has what we would call a fingerprint, and it's their atomic spectra, and they look at the wavelengths of energy coming off of each element. So somebody named Moseley, he looked at the periodic table and using X-rays, he was able to look at the diffraction and look at the elements individually based on their atomic number. So he found that each one had a different wavelength or frequency. Again, it's like sort of like a fingerprint where each element is completely different. So this is how we will go up into space, and not go up into space, but we can send light signals into space, and we could actually see which wavelengths come back, allowing us to detect what are on other planets. So it says each element absorbs light at a specific wavelength unique to that atom. When astronomers look at an object spectrum, they can determine its composition based on these wavelengths. That's called spectroscopy. And again, you could point a light at Mars, and based on the frequency that comes back, you can tell which elements on the periodic table are coming from that planet even though we are so far away. So it's very interesting that the periodic table, each element has its own fingerprint based on these wavelengths of energy as well. So it's very interesting. This here is from 1938 from MIT, where they were looking at wavelength tables for each of the elements. And it's really, to me, very neat understanding that these are wavelengths coming from sine or cosine, and that they're used to determine, even from long distances, very, very far away, exactly what elements are in space or inside of the sun or inside of a star. So just a couple more things that I thought I'd add to the video. Keep looking out for different things that are related to wavelengths. Seems like some similar patterns. Sound, electricity, light, color, they're all in wavelengths.